Hello students, good morning. This is the part 8 of our chapter Work and Energy. In this part, we will derive the general expression for the potential energy and also try to understand why work done by gravity or work done against gravity is independent of path. After that, we will solve some numerical problems related to kinetic energy and potential energy. Students, if you have not watched the earlier parts, then please watch them and then come to this part. Before going in detail with this part, let me recall you the concept of mechanical energy that we have covered till previous parts. So what is mechanical energy? I have explained you already. Mechanical energy. Students, I have told you that mechanical energy is possessed by an object when it has a capability to apply certain force on the other object such that the object get displaced in the direction of the applied force. In this way, this energy can be possessed by an object based on three categories. First, due to motion. Due to motion of the object, and you know the energy possessed by an object due to its motion is known as kinetic energy. The other name for this energy is kinetic energy. Okay students, the second type of energy or mechanical energy is due to change in configuration. Due to change in configuration. Configuration means shape and size. So due to change in shape and size. And students, you know the energy possessed by an object due to change in its shape and size is known by the name elastic potential energy. Elastic potential energy. And the third type of mechanical energy we have due to change in position. Change in position means we can say when an object is raised to a certain height from the ground level, then some energy is possessed by that object, and this energy is again named as gravitational potential energy. Okay, students? Gravitational potential energy. So we can say the mechanical energy is classified as kinetic energy, and these two energies are combinedly known as potential energy. Okay students, so in this way we can define mechanical energy as of two types, kinetic energy and potential energy. That's why we can write mechanical energy, that is ME, is equal to sum of the kinetic energy KE plus potential energy P. Kinetic energy plus potential energy P. So this is the relation between mechanical energy, kinetic energy and potential energy. Mechanical energy is equal to sum of the kinetic energy and potential energy. Okay students? Now we will try to derive the general expression for potential energy. Okay students, so here we can write general expression for general expression for potential energy. general expression for potential energy. Okay students, now let us suppose students, this is the ground level. This is what? This is the ground level. Okay, on which an object of mass m is kept. There is an object of mass m kept on the ground level. Now students, you know the weight of this object, which is equal to m into acceleration due to gravity g, is acting downward. Mg, weight of this block is acting downward. If we have to raise this block by a certain height, then we must have to apply a minimum force equal to its weight, that is mg. Okay students, now what we are going to do, we apply a force equal to its weight, that is mg, but in upward direction, and try to displace it by a certain height h. Now let us suppose we apply the force and the block shifted to this level. Okay, let us say this is the height, h, through which the block is raised. Okay students, so we have applied the force F, in vertically upward direction, which is equal to mg, and the body get displaced from the position A to the position B. Okay, now here we can write force applied capital F equals to mg, vertically upward. Okay students, now what is the displacement? You know, displacement is from initial to final position. So displacement is equal to AB, that is from A to B, and AB is equal to h here. So here the displacement is also in this direction. Okay, and the force is also in the same direction. This is force and this is displacement. This displacement here equals to h. Okay students, so what we can write, let us say W amount of work is done against gravity in order to displace this block from the position A to the position B. Then what we can write, the work done W equal to, you know the formula, F into S cos of theta. So here the F equals to mg, so we can write mg. The displacement S is equal to the height through which the block is raised, so here we can write h into cos of theta. Now here you can see that the direction of force and direction of displacement both are in same direction. It means theta equals to 0 degree. So here we can write cos of 0 degree. Now let us put the value. So mg h, and cos of 0 means positive 1. So it is equals to mg h. So this is the amount of work that we have done on this block in order to raise it through a height h above the ground level. Okay students, now students, you know the work that we have done in order to raise this block from the ground level to a height h is stored in the form of potential energy in this block. Why I am saying potential energy? Because here in this case we have done work against gravity, and you know the work that we are doing against gravity in order to raise an object through a certain height above ground level get stored in the form of gravitational potential energy. So it means here this work done, that is mgh, is stored in the object in the form of potential energy. So what we can write? Since this work done in raising it through height h stored as potential energy, so we have what? We can write the potential energy PE or EP, potential energy EP equals to the work done, that is mgh. So this is the formula for potential energy. Potential energy is equals to m into g into h. Okay students, what does this expression tell us? This expression tells us that the potential energy in raising an object through a height h is directly proportional to mass of the object and height through which it is raised above the ground level. It means if we increase the mass of the object, then potential energy will also increase. If we raise an object through a greater height, then more potential energy is stored. Now students, the general expression that we have derived for the potential energy is EP equals to m into g into h. Okay. With the help of this expression, what we can write first, the potential energy EP is directly proportional to mass of the object m. What is m here? M is the mass of object. What does it mean? Suppose students, we have two objects of mass m1 and m2. If we have to raise these two objects, and here m1 is greater than m2. Now if we have to raise these two objects through the same height, then we require more amount of work to be done on the object m1 because of its greater mass. Okay, and if we are doing greater work, then it means greater potential energy gets stored in the object of mass m1 because of larger mass. Now the second relation that we can write with the help of this expression is that the potential energy EP is directly proportional to h. What is h here? H is the height through which the object is raised above the ground level. So we can write directly proportional to the height of object above the ground level. What does it mean? Suppose you have to raise an object of certain mass through a height of 1 meter and again through a height of 2 meter. Then in which case you require to do larger work. First you have to raise through 1 meter and then you have to raise through 2 meter. So very obviously with the help of this expression, that is potential energy is directly proportional to height, we can say we require more amount of work to be done if we have to raise the same object by 2 meter as in case of 1 meter. Okay, so it means that greater the height through which we raise an object, greater amount of work should be done on that object. And if greater amount of work is done on that object, then it means greater amount of potential energy gets stored in the object. So this expression tells the potential energy is directly proportional to mass of the object and also the height through which it is raised above the reference point or above the ground level. Okay students, now we will come to the next topic, that is why work done by gravity or work done against gravity is independent of path. Means work done will remain same, does not matter what path we choose to raise it through a certain height. Let us try to understand with the help of two situations. Here in these two figures you can see that we have chosen two paths to raise the same object of mass m by the same height h. This is the path 1 and this is the path 2, as you can see here. Okay, so here when the block is placed on the ground floor, then you know the weight of the body, which is equal to mg, is acting downward. If we have to displace this object through a certain height h above the ground level, then we require a minimum force equal to mg to be applied in upward direction. So in order to displace this object of mass m through a height h above the ground level, we apply a force equal to mg in upward direction. So we have applied the force F, which is equal to mg in upward direction. Okay, such that the body gets displaced from the position P to the position Q, and it is obvious that PQ, that is displacement, is equal to h. Now here if we want to find the work done in order to raise the object from the point P to the point Q, then what we can write? Work done from P to Q equals to, the formula we have, F into S into cos of theta. Is it visible? F into S cos of theta. Okay students, now see here the force F equals to mg, so what we can write? Mg. In place of S we can write the displacement PQ, which is equal to h, so here we can write h, and cos of theta. Then what is theta? This is the direction of force and this is the direction of displacement. Both have the same direction, so we can write theta equals to 0 degree. So here cos of 0 degree. Now you know cos of 0 equals to 1, so it is equals to m into g into h into plus 1, so it is equals to mgh. So we can write mgh amount of work to be done on the object such that it can displace from the point P to the point Q. Okay. Now let us see the situation 2. In this case, we have chosen the another path 2. What does it mean? It means that suppose this is the object, then first we take it from A to B like this, then from B to C in this way, again from C to D this way, from D to E in this way, and again from E to F. Okay students, now we are going to find the work done in this case. So let us say this is the position P and this is the position Q. Again PQ is equals to the height h. Here we can write work done from P to Q is equal to work done from A to B plus work done from B to C plus work done from C to D plus work done from D to E and last work done from E to F. Now let us try to find work done in each of these cases. So work done from A to D. Here you can write the force equal to mg. Mg is in upward direction and the displacement is equal to AB and that is also in upward direction. So what we can write here? mg into AB into cos of 0 and cos of 0 you know equal to plus 1. Now from work done from B to C, work done from B to C. Then this is the displacement. This is the direction of displacement and the force is in upward direction. This is the direction of force. So here you can see the angle between them is 90 degree. Okay, so what we can write here? F, that is mg into displacement is what? BC into cos of 90 and cos of 90 you know 0 plus work done from C to D. Let me erase it. Now work done from C to D. Here you can see this is the displacement, this is the direction of displacement and this is the direction of force which is equal to mg. It means force and displacement both have the same direction. So the theta will be 0 degree and cos of 0 means 1. So what we can write here? Force, that is mg into displacement is what? CD into cos of 0 and cos of 0 equal to plus 1. So here we are not writing. Okay. Now work done from D to E. D to E. So this is the direction of displacement. This is the direction of displacement and the force is again in upward direction. So here you can see the angle between them is 90 degree. Angle between them is 90 degree. So what we can write? mg force into displacement dE into cos of 90 and cos of 90 is 0. Okay students? And the last work done from E to F. Work done from E to F. So this is the direction of displacement, this is the direction of displacement and this is the direction of force. Both have the same direction. So again theta will equal to 0 degree and cos of 0 is positive 1. So what we can write? mg, that is force, into displacement. Displacement is EF. I hope it is clear, okay students? Now let us see what is going on. Now here you can see that, let me erase these things. Okay, now this is the part 2. We have part 2. Okay, now here what we get? mg into AB. This term becomes 0. After that we have mg into CD plus mg into DE into 0. So this term vanishes and last we have mg into EF. Okay students? Now if we take mg common here, then what we have within bracket? AB plus CD plus EF. Okay students? I hope it is visible. Now mg into within bracket AB plus CD plus EF. Now what is the value of AB plus CD plus EF? This is AB, this is the AB. Now CD, this is CD, AB, this is CD and EF, this is EF. So it is clear from the figure that AB plus CD plus EF comes out to be H. AB plus CD plus EF is again equal to H. So in place of AB plus CD plus EF we can write here mg as it is into h. So in this case again we find that work done from P to Q equals to mgh as in the previous case. As in this previous case, that is from path for the path 1. So with the help of these two examples, it is clear that work done does not depend on path, because in both this equation we have done the same work mgh. So we can write or we can say the work done against gravity is independent of path that we follow in order to raise it through a certain height. Okay students, now we will try to solve some numericals based on kinetic and potential energy. Here in this question it is given an object of mass m moving with a constant velocity v. How much work should be done on the object in order to bring the object to rest? So first let us select the information that is given here. So here what we have given, we can write there is an object of mass m which is moving with a constant velocity v. So we can write the initial velocity is given, initial velocity is equals to what? V. Okay students, initial velocity is given. After that we have given how much work should be done in order to bring the object to rest. It means finally the object stops. So if the object stops, then it means final velocity equals to 0. Now students, let us suppose W amount of work should be done on the object in order to bring it to rest. Let W be work done on object to bring it to rest. Now we know the mass of the object, we know initial velocity, so we can calculate the initial kinetic energy of the object. So we can write initial kinetic energy EKI equals to half m into initial velocity. Initial velocity is v, so square of v. This is the initial kinetic energy. Now final kinetic energy is Final kinetic energy is EKF. That is half m into square of final velocity. Final velocity is 0. So here we can write square of 0. So this is equal to 0. So we have calculated the initial kinetic energy and final kinetic energy. Now remember the work energy theorem. Work energy theorem tells that net work done on an object is equal to change in kinetic energy. So by work energy theorem, we can write the work done W equals to change in kinetic energy. So W is equals to change in kinetic energy means final kinetic energy minus initial kinetic energy. So here we can write EKF minus EKI. Now let us substitute the values. So what we have, EKF is equals to 0. So 0 minus EKI, that is initial kinetic energy. So it is equals to half mv square. So what we get? We get the work done W equals to minus half mv square. So this is the amount of work that we should done on an object in order to bring it to rest. Okay students? So this is the solution. Here negative sign means work done is negative. Work done negative means the direction of the force and displacement is opposite to each other. Okay. Since it is clear from the question that we are resisting the motion because we have to stop, so we are resisting the motion. That's why the work done is negative here. Now let us see the next question. Calculate the work required to be done to stop a car of 1500 kg moving at 72 km per hour. So first let us collect the informations given here. So here in this question we have given mass of the car, mass of car m equals to 1500 kilogram. The initial kinetic energy, initial velocity is given as 72 km per hour. Initial velocity equals to 72 km per hour. Since it is given in km per hour, so first we have to convert it into meter per second. So it is written as 72 into 5 by 15 meter per second. 15 4 times 72, 4 into 5, 20. So it is equals to 20 meter per second. Okay. Now we have to calculate the work required to stop a car. Stop a car means the final velocity will be 0. So final velocity equals to 0 meter per second. Okay. Now since we have the mass and we have the kinetic energy, we have the initial and final velocity, so we can calculate the initial and final kinetic energy also. So let us calculate initial kinetic energy. E A I equals to what? Half into half mv square. So this is equals to half into mass of the car 1500 into V. V means 20 square. And with this what is joule. So it is equals to 1500 by 2 into 20 square means 400 joule. So it is equals to 15 into 2, 30, and we have 4 zeros. So this is the initial kinetic energy. Now let us calculate the final kinetic energy. Final kinetic energy EKF equals to half mv square, but the final velocity is 0. So what we can write, half into 1500 into 0 square, that is equals to 0. Okay. Now again by work energy theorem we know that the work done W equals to EK F, that is final kinetic energy minus initial kinetic energy. So we can write work done equals to final kinetic energy is 0. So 0 joule minus how much it is? 3 into 10 to the power 5. 3 into 10 to the power 5 joules. So it is equals to minus 3 into 10 to the power 5 joule. So this is our answer. 3 minus 3 into 10 to the power 5 joule. Now let us see the next question. The next question we have: a light and heavy object have same momentum. Find out the ratio of their kinetic energies. Which one has a larger kinetic energy? Okay, students. So let the light and heavy object having the mass m1 and m2 respectively. Solution. Let the light and having object of masses m1 and m2, means m1 is the mass of lighter object and m2 is the mass of heavier object, having same momentum b. Okay, students. Now let me remind you a relationship between the kinetic energy and momentum. We have learned the kinetic energy Ek equals to P square, that is where P is momentum divided by twice of mass of the object. So we are going to use this relation in this problem. So with the help of this expression we can write the initial kinetic energy of first object Ek1 equals to momentum square, that is P square, divided by 2 into mass of the lighter object. Mass of the lighter object is m1. So here we can write 2 into m1. In the same way, the kinetic energy of the heavier object of mass m2, we can write Ek2 equals to P square divided by 2 into mass of the heavier object, and mass of heavier object is m2. So we can write 2 into m2. Okay, students? Let us say this is equation number 1 and this is equation number 2. Now divide equation 1 by equation 2. Then what we get? Ek1 divided by Ek2 equals to P square by 2 m1 divided by P square by 2 m2. From here what we can write? P square by 2 m1 into 2 m2 divided by P square. So P square cancel out, 2 and 2 cancel out, and what we get? We have here Ek1 divided by Ek2 equals to m2 by m1. So this is the ratio of the kinetic energy of the lighter object and heavier object. When you observe this relation carefully, then you observe that the ratio of the kinetic energy of lighter object to the heavier object equals to ratio of the mass of the heavier object to the lighter object. It means there is an inverse relationship between the kinetic energy and mass. So we can say, if this is the inverse relationship, so we can say lighter mass will have greater kinetic energy. I hope students it is clear to you. If kinetic energy we can write inversely proportional to f, then what does it mean? Lesser the mass, greater the kinetic energy. Here the m1 is lesser, so we can write lighter mass will have greater kinetic energy. Okay, students? So thank you. In the next part, we will discuss the transformation of energy and conservation of energy.